I'd like to build a bit more on our ground state electron configuration, so those lowest energy versions of how electrons will arrange themselves in an atom, and talk about valence electrons and their valence electron configuration. So electrons in all the sublevels that are in the highest principal energy shell are called the valence electrons. So these are only going to include s and p orbitals because we'll always fill the next energy levels s orbitals before we fill the d orbitals for any level. So our valence electrons are always s and p orbitals of the highest n quantum number in an electron configuration. Anything else that isn't a valence electron is called a core electron. And the difference here is those core electrons are in closer to the nucleus than the valence electrons, which means they have a little bit more penetrating power. The valence electrons are special because they have the highest probability of being further away from the nucleus, just by the nature of being the highest n quantum number. And then because of that, they are less stable than all the other electrons. They experience more shielding than all the other electrons too, because they are on kind of the outskirts of the atom, and they can penetrate in, but their probability of being closer is much lower than their probability of being further away. And so they're the least stable and they're furthest away from the nucleus, so they experience the least effective nuclear charge. And since they're that far away, these are the electrons that interact with the rest of the world. The core atoms are kind of shielded from the world by those valence electrons. And so when we have two atoms collide together in a chemical reaction, what's happening is those valence shell electrons are what are interacting, and they are either being shared and forming a bond or transferring electrons, but that the chemistry occurs in the valence electrons. And that's why, as chemists, we care about them so much. So let's look back at strontium, our example we were working with. I have its electron configuration written again here at the bottom. And if I wanted to represent just the valence electrons, it would be the highest n. And so looking at this, the highest n is 5. And so, sorry, there we go. So it's not necessarily the highest in energy, right? Because if I had then 4d electrons there, that 5 would still be the highest n number. And so my valence electron configuration just includes the 5s2. And I've here abbreviated it with my noble gas that's nearest to it. And so this just represents my valence electrons. And so if you're asked to provide a valence electron configuration, just write out the electron configuration for the n with the highest value, and it'll be just s and p orbitals. Looking at this at the periodic table is helpful for me, at least. The periodic table can kind of be grouped based on these electron configurations, and the grouping for the electron configurations is thinking about the element as what is the last electron you fill using the Pauli exclusion rule and Hund's rule and the Aufbau principle. And so that last electron filled in our electron configuration or orbital diagram kind of defines the block of electrons you're working in. And so any element that is in groups 1 and 2 are always going to have the last electron filling an s orbital. Anything that is over here in the second half of, or the next 6 of the main group elements, all of these elements are filling electrons in the p orbital last. Anything in the transition metals is filling a d orbital last, and anything that's in our lanthanide and actinides is filling an electron in the f orbitals last. And so these are blocks of elements that correspond visually to that last electron's orbital placement. And so if I just look at any element on here, I should be able to quickly say, oh, well, it definitely has these electrons in this orbital. So if I look at osmium, I can say, oh, well, yeah, osmium's going to have valence electrons in the d orbitals. The last one I fill would be in a d orbital. And then I can get a little bit more information because it's in row 6. I know that the last electron filled is going to be in the 5d orbital. And because it's in this group right here, I can say that, well, I know I'm going to have 1, 2, 3, 4, 5. I'm going to have 6 electrons in the d orbital. So I can tell you right now that the the last or the highest energy orbitals in this diagram would be 5d6. And so the periodic table can kind of be a useful way to shortcut these electron configurations after you get used to it. So your group number, which is that right here, that group number is always going to be the number of valence electrons if it's in A. And so that's just going to apply to these elements right here. And if it is in like this osmium, if it's in one of the B categories of group numbers, then what we're going to be looking at is always having 2 valence electrons that are coming from that s orbital, and then the later electrons that are at a higher energy level are filling in technically at the core because they have a deeper penetration towards the nucleus, even though they're high in energy. Also, the length of each block of these elements will correspond with the number of sublevels, like the number of electrons in the sublevels. So S electrons can always have, or the S sublevel, or L equals 0, can always have 2 electrons. L equals 1 can always have 6 electrons and 3 orbitals. For D, they can always have 10 electrons for L equals 2 in 5 orbitals, and you can have 14 and L equals 3 within the 7 orbitals that it creates. And lastly, the period number, so that was this 6 for osmium, is going to correspond to the highest principal quantum number for the valence electrons. And for something like osmium, that would be written, I'll give you the abbreviated one. It would be xenon, and then 6s2 5d6 would be its abbreviated electron configuration. You can see that that period number corresponds to its valence electron quantum number, n, though not the highest energy, because the Ds would be higher in energy for 5d.